the outside will be plus and the inside will be plus. So look when you see this. Now what is inside of this thing is a transformer, by which we mean that it's changing the level of the voltage. See, out of the wall comes 120 volts. Now suppose you don't want 120 volts, suppose you want something like 10. What do you do? Well, with alternating current, what you can do is you can put this into a coil with a lot of turns, and then you can put this one into a thing with a few turns. In fact, the ratio of turns will be 12 to 1. I just did it in my head because it's the ratio of 120 to 10. I picked a good number there. So the ratio will be 12 to 1 turns, and you go this. And then this will come out. Again, it'll still be AC because I started with AC. But it'll give me 10 volts. That's the trick. Then I can do some other things, like, for example, if I really want DC, what I can do is I can put it through a thing which passes current only in one direction. So this is coming something like this, 120 volts. Well, that means it's something like 120 over here, and it's going plus minus like that. So what I can do is I can put it through this, which will clip off and let it pass only the pluses. This is called a diode or rectifier. Well, it's a rectifier. That's the most important. How you rectify is something else. To rectify means to make right, but in this case, right means only going in one direction. So it rectifies, and so I get only pluses. That's good, because maybe my device only wants to see pluses. Well, you know, I can make the plus any which way I want, but I want it steady. And then what you can do is try to smooth it out. Just smear, you're putting something which drags this out, which would be actually a capacitor. Because as we know, if you put charge on a capacitor, it holds it. So we can put this charge on a capacitor, and it will sort of just build up, and it'll be held for a while. And then we can put it out to our little thingamabobby here, this thing. Okay? So this is what goes on in your little box here. The little box contains, well, it's a wire. It's got this, and out comes this wire here. It contains this capacitor. And it's doing all this little work for you. Now, the way so you start out with 120, we will transform it down to about 10 AC. Then we will put it through a rectifier to make it all come plus. Then we'll smooth that out, and then you'll have your nice smooth 10 volts. There are two elements here that are special to us now. One is this rectifying thing, which we won't talk about. Maybe we can get to that when we talk about how you can make solid-state devices which will pass current all in one way. That's a pretty good trick, but we can do it, fortunately. So let's just talk about this part, just the transforming of the 12 volts down to close to what we want. And the trick is very straightforward. And that is that if we can get, you see, the point was that what we're going to use is the magnetic flux varying in time is going to produce this EMF. We're going to, and if so what we can do is we start out with our 120 volts, say. We put it on this wire, and we create a current through the left side spool of wire, and it produces a magnetic flux through this spool of wire. So, but what we want to do is link that magnetic flux with the other spool of wire. So we can put something like iron. Iron will do that. So it magnetizes, and it sort of holds the magnetism, and we can make a kind of a magnetic circuit of iron around like that. And on this side, we put just the 12 times less number of turns, like that. So if you have a certain amount of flux passing through here, see, this should really be, this is the amount of electromotive force generated for each turn of loop here, because every one of these loops has a flux passing through it. And we have n loops in a row, in series. So actually, the voltage that we're going to get is n times the voltage in one loop. I think that's the question you asked. When a dipole has n turns, how big is it? Well, it's current times area for one loop. But if you have n loops, they add up. Each one of them produces a dipole. And so they add up. Similar things happening here. We have this flux passing through a loop, but there are n of them in series. So you're going to get a voltage at the end here, which is n times the voltage of 1. Likewise, when you go over here, you have the same flux passing through here to give you the field, which is n times well, no, I think I want to do it this way. No, I think I want to do it this way. I want to put it this way. I have n. This is n. Yeah, I have n. Yeah, this will give me the voltage on the what's called the primary side. This is the primary input side. And because of their n turns, I will get E on the primary side, or n times the voltage of one of these guys. And on this side, I have the voltage that's created here is little n times, or it'll be little n times the d phi dt. So, which is the voltage on the secondary side. So if I can get the voltage on the secondary side over the voltage of the primary side, it will be proportional to the respective numbers, n over n. So this is the law of the transformer, and that is that if you want a voltage on this side, the primary side, to the secondary side is proportional to the number on the primary side. Let me make it more general, because it could be more or less than on the secondary side. So it's proportional to the number. See, the idea is the same flux passes through both. If you have more turns, you get more little voltages in series. You get more voltage created on this than on this. And that's how you can knock the voltage down here from 120 to 10 by putting 12 times as many volts turns on the primary side than on the secondary side, and out will come the 10 volts. So that is very powerful. Very, yes, sir?
So energy loss?
No energy is lost. What happens? It's a very good point. No energy is lost. You lose the voltage, but you gain in current. So the power, this is a very important point. Thank you for raising it. Very profound point. The power that goes in, now here's a formula that you really must know, is the voltage times the current. Now this is a very important formula. For example, in a resistor, we've seen this before. I think I wrote before, power is I squared R. But it also comes out of this formula because in a resistor, V is equal to IR. Therefore, if I substitute for V, IR times I get I squared R. So this is the power in general. And in different devices, you'll get different power. For example, in a capacitor, the voltage is, how does it go? C equals Q over V. So the voltage is Q over C. You've got to be a little careful here. You'll get an extra factor of 2 because it builds up in a funny way. But let me just substitute V Q over C. I is dq dt. So this is a way of getting the energy. This is power. If you want to get energy, you multiply power times time. You would have to integrate that, and that's how you get the energy stored in a capacitor. In other words, if I were to integrate for a capacitor, power times time, integrated from 0 to when the thing is charged, I would get the integral of Q over C integrated, and I would get Q squared over 2C, which should agree with what I wrote before for the energy. If I write Q is equal to CV squared over 2C, I get CV squared over 2. And V I can convert to electric field by dividing by the distance, and I can then get that the energy in a capacitor is the integral of the power, and it's CV squared. And a similar thing can be done with the inductance. If I put in the current, the voltage is L di dt, you can get that the energy in a capacitor, in the inductor, as I showed here, is considerable. So the usefulness of this transformer is enormous. You have no idea how much important it is in your lives. For example, you start your car. How does the thing start? Well, you have a battery, 12-volt battery somewhere under the hood there, hiding, and but somehow it has to create a spark in the cylinder of your engine. You know how that works. They put in gasoline as a vapor, and then you compress it with the pistons, and then you have to fire it, which pushes the piston down and gets the wheels rolling. That's how your car works. But you have to get a spark. Now, in your ordinary gasoline engine, there actually is a literal spark plug, which has little points. Have you ever seen a spark plug that has a little gap and you put a voltage across? But you need a pretty big voltage. 12 volts won't do it by itself. It just isn't enough. So you have to boost it up. And the way you boost it up is that you've got to get it changing with time, so that you make an alternating current, and you put that on this side of the transformer. You get a dV/dt on this side. If you have a bunch of coils on the other side, you'll make a big dV/dt, and that's big enough to make a spark. So that's what this is, ignition coil of your car. If I took this battery, let's just for fun, nobody's ever done this before. Let me just put the voltages across here. Nothing, no spark at all, right? But if I put it here, now what's inside of this guy is that 6 volts is going to go onto a little coil like this, 6 volts. But you're going to have a lot, in fact, it's wrapped around this, a lot of turns. So you're going to boost this up from 6 volts to thousands, the ratio being about 1,000. And if I do that, I can make 1,000 volts jump across. So that's what's going on in here. See that? Can you see way back yonder? It's not much, but it makes your car run. So, yeah. So what you're doing is, of course, it's all about timing. You have to time it when the piston is here and the gas is there, and the spark plug fires at the right time. And so that's important. And then when you get home, you turn on the lights, and the lights go on. And why is that? It's because there were transformers all along the line from the power plant to your house. I wish I had the pictures on my, so I do have them at home, I'm sure. So what happens is you have the power plant generating electricity, but they don't want to transmit the electricity at low voltage. It turns out that if you go hundreds of miles with wires, you get these I squared R losses in the wires, which you can make less by raising the voltage with a transformer. Again, this will be a few turns with a lot of turns. Lots of turns. So you boost this up from whatever the generated power plant, maybe 60 volts, to hundreds of thousands, maybe 500,000 volts. That's why you should never touch one of these, go across one of these things. You might transmit at 500,000 volts by stepping it up. We call that step-up transformer, till you get to the city. Now you don't want to plug in 500,000 volts into your appliances, because that might cause a lot of smoke and unhappiness. So you have to step it down to what we get out of the wall here of about 120 volts. So what you have to step down, meaning you would start with a lot of turns and have a few turns. And when you go home, if you look up on the power poles, you'll see these sort of canisters. Those are transformers where high voltage, maybe 600, maybe 1,000 volts are coming in, and they're stepping it down. Out of this will come 120 or 240, which will run your appliances. So this is very, very important. And the key thing, we can go through the numbers, but the goal here is to reduce the losses in the power line. So you transmit at very high voltages by stepping up from the power plant, and then you step down when you get near your house to voltages that are not so potentially lethal or disastrous. So what else do we talk about these wonderful things? I mean, this is really... the last thing I did want to make sure you piece together and have a good grasp is the differences among these elements that we've encountered so far. We have them all that we use in electronics. R, we saw C, and we saw L. I think I went into some of this before. A resistor is a little object that looks like this. Sometimes, it depends on what you're doing, but we have that it has a certain, the point that I want to make, the similarity is that these are all determined by the geometry and the material in them. Now you can jiggle with the geometry in some cases. You could, in the case of the capacitor, it's easiest. You can just move the plates with respect to each other, in or out, make them larger or smaller, slide them with respect to each other. So that affects the geometry. And the material depends on what you put in it. Now in the resistor, the resistance is given by the resistivity, which is a property of the material. Maybe I should have said material and geometry in the other order, because we always write them material and geometry. So I just want to show you the nice pattern of things. You have the material, that is sort of the clogginess of the material. If you make it out of, sometimes you can make it out of, there's a thing called wire wound resistors. They're just wires, which, the wires don't have much resistance, but if you make them thin enough and long enough, you can actually make it into a decent resistor. Or it could be a compacted graphite with a little glue in between, so it's kind of cloggy. So that's the material, rho, its length over its area. The longer it is, the more resistive. The bigger the area, like a pipe, the less resistance it is. So this is the geometry part. The capacitor looks like that, and it's for the parallel plate, it's epsilon naught over the separation, d maybe. So the epsilon is the material part. You could put some other stuff in here which would have a relative boosting factor. So the material would be put into there. And here is your geometrical factor. And the inductance is, well, for the solenoid, I think we had that the flux was equal to n times mu 0 I. So the inductance is phi over I is n mu 0. So for an inductor, you have your mu 0 times the number per unit length. And you could put in this factor that we brought up before, the relative permeability of some material that you could stick in the inside of the inductor. Like if you put a magnetic material, a strong magnetic material, you'll get more flux, and because it will contribute flux. And then the material will be that factor, and then this is the geometrical factor. So I just wanted you to see that there is a pattern here. The other thing is, the other thing you have to be very careful about is that as far as the energy goes, I'm glad somebody brought up the power thing, you must remember that here energy is not stored, it's dissipated. That is to say, an ideal resistor just gets warm when you put current through it. Power is equal to I squared R. And here, the energy is stored. And I think I derived that over here. It was something like a half CV squared or something like that. Energy is stored. And we've seen that where I discharge a very large capacitor and you got a spark. Here also, we have this guy here where energy is stored, and I think it's Li squared over 2. It's a very similar thing. You see you have square of the current, square of the voltage, square of the current. You have the factor of the object, C or L. So there is this pattern. It's all in my notes, but it's good to see this all as a whole. Oh, I think we're going to be kicked out of here. I'm surprised they haven't descended on us. The lecture today is kind of interesting. It's from somebody from this project SETI, looking for extraterrestrial intelligence like signals. And the professor, I think it's going to be a debate. The professor who has found a lot of planets, Marcy, has found planets out there. And I think he's skeptical whether we'll ever make contact with people. So you can maybe hear that debate if you want to save this. Or I'm going to have an office hour upstairs, which will be available to you.